Hello, I'm Alex Arnold. My teammates are Tanner Korb and Anna Wang. This is our presentation on the Refrigeration Lab 1. Machine Chillers Incorporated has developed a cooling system based on a vortex tube. Our engineering firm has been hired to review the system and determine its capabilities. Using the system in this image and air as the working fluid, an accurate model of the system is to be created. The developed model should successfully establish a relationship between the input pressure and other key parameters, such as the cold output temperature and the cold output mass flow rate. Heat transfer analysis will also be conducted on the mass block to compare the experimental mass of the block to its known mass. Finally, the thermal resistance of the insulator that was used will be solved for and compared to that of styrofoam.
The left side is a schematic of the cooling system, while the right side is an actual image of the cooling system used in the experiment. Firstly, incoming compressed air is set to room temperature using the heat exchanger. The air then enters a vortex tube, which has a cold and a hot output. The cold output is fed to the aluminum block, which is covered with an insulator, to cool it down. Station 1 is where we're bringing air into the system. Station 2 is between the heat exchanger and the accumulator. Station 3 is right before air enters the vortex tube. Here we've taken a pressure and temperature measurement, and we're assuming that this is ambient pressure and temperature. Station 4 on the hot side is where hot air is leaving the system. Station 4 on the cold side is where cold air is about to enter the load. We've taken a temperature measurement at both the hot and cold side of Station 4. A temperature reading was also taken at the load and at Station 5 where cold air is about to vent out. We want to examine the energy transfer in the load and also characterize parameters such as thermal properties of the block and the transient response of the energy transfer. A pressure reading was also taken at Station 5, which can be assumed to be equivalent to the pressure at Station 4 on the hot side. Some of the assumptions made during this experiment are the lumped mass model to represent the energy change over time. Also, the outside of the insulation is at ambient temperature and heat transfer rate due to ambient heating is small. Unit conversions, constants, and the measurement of length, area, and ambient temperature and pressure are assumed to have negligible uncertainties, and it is also assumed that the pressure drop across flow meters is negligible.
This table shows the data collected at the steady-state segments of our parameters, which are the inlet pressure of the vortex tube, the outlet cold temperature of the vortex tube, the outlet hot temperature of the vortex tube, cold vortex tube outlet flow rate, and the hot vortex tube outlet flow rate. As expected, the flow rates of the cold and hot outlets both increase when the inlet pressure increases. It can also be noticed that the hot outlet temperature increases more quickly than the cold outlet temperature decreases. This is because the cold outlet flow rate becomes increasingly larger than the hot outlet flow rate as pressure increases. Therefore, this data holds true for the idea that the hot air temperature increases as the cold fraction, which is the ratio of the cold outlet flow rate to the total flow rate, increases, and why cold air temperature decreases as cold fraction decreases. These graphs show the natural log of the cold air temperature and the hot air temperature versus pressure. The uncertainty for the cold air temperature is greater than that of the hot, since these are log graphs and the uncertainty is based upon the inverse of the root value of the temperature. Therefore, it is expected that the cold air would have greater uncertainty since its root values are smaller. These graphs show the natural log of the hot and cold air mass flow rate versus pressure. The uncertainty of these two graphs are very similar since their root values are also very close.
So next, we calculated the thermal resistance for the insulator. Thermal resistance is how well an object resists heat flow. At steady state, we can assume that the heat transfer rate of air is equivalent to the heat transfer rate due to ambient heating. So using this, we can set equation 1 equivalent to equation 2 and solve for insulation thermal conductivity and use that to solve for the insulation thermal resistance. We found that thermal resistance was higher at 50 psi than 80 psi, that both of them were lower than the thermal resistance of styrofoam. This may be because the insulation in our cooling system doesn't cover the top of the block.
Next, we represented the relationship between the temperature and time using the system cooling equation. For the first system with 50 psi pressure applied, there's a small amount of data taken for the transient regime. This results in a fit that is not all that good because the section is almost linear and the exponential system cooling equation isn't the best choice for linear regression. This is the system at 80 psi, which more data points were taken, but there is actually an anomaly in this data, which can be seen outlined by the circle, which caused the system cooling equation to not fit quite as well due to the small bump where the system actually reaches close to the steady state temperature value and then slightly increases, giving data that may not be accurate. The tau and beta values are also displayed for this system.
So next we calculated the mass of the block. In the transient response, the heat transfer rate of air is equivalent to the energy change rate of the mass. The heat transfer of the mass was solved by using the trapez function in MATLAB to take an integral of the heat transfer rate of the mass. Using the lump model, we can solve for the mass of the block. The area of the mass of the block was solved using the EPA analysis. This value, in addition to the actual mass of the block, is shown in the table on the screen. The calculated mass of the block is lower than expected because the specific heat might not be accurate for our material since the actual aluminum block may have impurities. The lump model may not also be an appropriate assumption for evaluating the block in the transient response. So just as a summary of our results, we have found the measurements for the steady state behavior of the vortex tube. We've also found the relationship between input pressure and cold output temperature, cold output mass flow rate, hot output temperature, and hot output mass flow rate. We've also found tau and beta for both 50 psi and 80 psi of compressed air. And we've also solved for the thermal resistance and the mass of the block and compared it to the actual mass of the block. So knowing all these parameters is critical for the next steps in this experiment. So next we're going to analyze the cooling system with an integrated compressor as a source for the compressed air. We're also going to evaluate overall energy efficiency versus the input torque and speed from the motor. And we are also going to calculate the conductivity coefficient of air.